Good afternoon. I am Jacky from ESD Acoustic. I'm here to share a new phase plug design method. So what's new? The basic deductions. First, the horn expansion should start from the entrance of the phase plug, not the exit of the phase plug or the throat of the driver. Second, the incident wavefront from the phase plug to the horn should not be simply considered to be flat, but dependent on the horn curve. For curvatures like track checks, the wavefront is supposed to be an arc. Third, different slots in concentric annular ring phase plugs should be calculated based on equal phase method rather than equal path length method, because air pressure can be different in each slot. Thus, the speed of sound differs as well. If you have any questions, you can ask at any time. Okay. So the starting point of the horn expansion, due to historical and industrial reasons, current drivers and horns are always designed separately, tested separately, and teamed up as well. So, for example, if you have a T80 driver like 2003, 4003, you team up with a horn that you like, and you try different kind of combination and feel, okay, this is better, this is not, but that's not what it is supposed to be, because the driver itself has a curvature of its own. It does not match any horn that you put together with it. This brings us to a question: should the horn expansion rate only be applied to the horn itself or the driver as well? I believe in the latter, and that driver and horns has to be designed together. So one horn model only matches one driver model. It is easy to see that the throat of the driver is merely an extension of the horn, so it should also follow the same formula applied to the horn. So as you see, the left one, the curvature from the horn to the throat of the driver is consistent, so it's very smooth. The right one, the horn is its own curvature, and the driver is its own curvature. So it has a sharp turning point at where they connect each other. So that way, the sound going from the throat to the horn will not have a smooth expansion. What about the phase plug then? When we talk about compression ratio, we are always referring to the total exiting area of the phase plug compared to the total surface area of the dome. But in fact, the compression is done at the entrance of the phase plug, where a big amount of air pushed by the dome has to be squeezed into much smaller slots. From there, all the way to the mouth of the horn, the air is always expanding and not compressing. By this logic, the slots of the phase plug should also follow the expansion formula of the horn. At each cross-section of the phase plug, total area of all slots should equal to that of the horn as corresponding level. So what does that mean? Is that, as you can see, on the left side is a horn curvature all the way down. On the right side, you have this phase plug, and this area is equal to this area. And this area should also be equal to this area, the combining cross-sectional area of each slot together. Like there are 4 rings that you combine the area of 4 rings together should be equal as the area of the horn at that level. In order to simplify calculation, designers used to assume that the incident wavefront from a phase plug to its horn is flat. While this assumption is true for some horn expansion curvatures, it is not universally correct. Take Tractrix curve, which is widely applied and praised, for example. It has curved wavefronts where the wavefronts are always vertical to the horn's inner surface. Therefore, at the exit of the phase plug, although the wavefront is very similar to a flat one, it is still slightly curved. Therefore, the exit of the phase plug should be consistent with this curve with wavefront. As you can see here, it's a typical Tractrix curve where you see the wavefronts are vertical to the wall of the inner wall of the horn. And that's the exit, and that's where the entrance is, so it's still slightly curved. Like before, we used to think that we can calculate as it's flat, but it is not. They're still slightly different. If you calculate as a flat one, the small difference at the entrance will make big difference at the exit. Therefore, this is an example of a phase plug designed to have a curved exit, where you can see at the exit of this phase plug, it's an arc, not a flat one. Okay. Another thing about equal path length versus equal phase. Current equal path length design method is based on the assumption that the speed of sound in each slot is the same, by which we can achieve phase alignment by making the length of each slot equal. This method also requires air pressure in each slot to be the same. So we try to approach this precondition by setting the width of each slot equal, and the distance between them equal as well, so that each slot has the same ratio of area compared to its nearby dome area. For example, here, this is a cross-sectional view of a phase plug where you have 4 entrances here, 4 slots. This slot takes charge of this area. So the air of around here from the dome to the slot mostly comes into this slot. This area always comes to this slot, and this area, so on. So you can see that in previous assumption, we always have the slot with the same width and the same, also the same width of the area that's in charge of. So that way the ratio remains stable, and the air pressure is also always the same between different slots. That way we can achieve the assumption that the speed of sound in each slot is the same. That's a precondition that we can calculate with equal path length method. However, equal path length method, it helps to simplify the calculation of slot entrance, but it has 2 drawbacks. First, since the outer slots are closer to the exit, with equal path length method, we have to twist outer slots into S shapes to achieve equal path length. But winding paths would increase distortion. What I mean is like this. So the path length from here to there, these 4, they are the same. Okay, but the problem, as you can see, is obvious. It's an S shape. The sound has to go an S shape from the entrance to the exit. That way, it surely creates more distortion. The second one is that similar geometry at the entrance potentially increases frequency selection characteristics, which would result in small peaks and valleys in frequency response, since we have same width at each slot, so it's similar geometry. So what if we adjust like this? Since the outer slots are closer to the exit, we can enlarge the width at the entrance of those slots. Thus, we will have lower air pressure and a slower speed of sound, then narrow the width at the entrance of inner slots so that they would have higher air pressure and faster speed of sound. By this method, we intend to adjust the arrival time of air in each slot from entrance to exit to be uniform. So last picture, we have 1.4 width of each slot. But this one, we have smaller width at the inner slots and bigger width at outer slots. So the air pressure will differ and the speed of sound will also differ. In the length, if the length of each slot from inner to outer is A to B to C to D, then we have to adjust the slot entrance in such a way that the speed of sound in each slot also becomes A to B to C to D. Thus, we can also achieve phase alignment without the two drawbacks referred above about the equal path length. Please remember that calculating the relationship between the width of the slot, air pressure, and the speed of sound is not linear. We also need to know that by changing one slot width, we change the pressure distribution among different slots as well. Therefore, precise calculation is beyond human brains and needs to be done by finite element analysis, like this. So this is a finite element analysis, and you can see clearly how the sound waves goes out. So here's a summary. In this new design method, we need only two factors to come to a unique solution: the curvature of the horn and the total area at the entrance of the slots. Once these two are determined, we are able to calculate the corresponding distance between the phase plug entrance and the horn mouth, and then everything else, because all components now follow the same one expansion formula. Design of the slots follow equal phase method, while precise calculation needs to be done by finite element analysis. Since the slots are curved, not straight, this kind of phase plug is not suitable for molding mass production. It is recommended to make this kind of phase plug with 3D printing technology. Okay, that's a showroom where we're at. You can hear the actual sound that this kind of method will make. We achieve 0.1% distortion at 1000 Hertz with a horn speaker. Thank you very much. Do you have questions? Not really? Okay, thank you.